So students, we just completed conservative and non-conservative force, and I told that to learn the basic meaning of potential energy, you must have to learn the concept of conservative and non-conservative force. I just completed this part in lecture number 3. If you don't watch, go back to the previous class, see the meaning of conservative force, then come back to this video. This is our lecture number 4, and in this lecture, what is the key point? In this lecture, we will discuss the potential energy, the meaning of potential energy, and we will see what is the relation of potential energy with conservative force. Then we will give the statement of principle of mechanism of mechanical energy, and we will prove the conservation law of mechanical energy in case of a freely falling body. So this is our today topic. So chalo shuru kora jak. So first of all, I think all of you know the basic meaning of potential energy. Potential energy is the energy associated with a body by virtue of its configuration or position. Okay, but there is no specific defined definition of potential energy. You know, potential energy is not defined. There is a definition, specific definition, that is the change in potential energy, and the change in potential energy is always associated with conservative force. You see the definition here. The potential energy is the energy associated with the configuration of a system in which the conservative force acts. There is no relation between potential energy and non-conservative force. Potential energy is always related to conservative force. So this is the definition. Now you know the classification of potential energy. Potential energy are classified in 3 categories. Number 1, that is the gravitational potential energy. Number 2, that is the electrostatic potential energy. And number 3, that is the elastic potential energy. And I told that the potential energy is always related to conservative force. You see, gravitational force is a conservative force, electrostatic force is a conservative force, and elastic of spring, a spring-like object, is also a conservative force. And what is conservative force? A force which is path independent, that is depends on the initial and final position only. So what is gravitational potential energy? When gravitational force acts, the potential energy due to gravitational force is known as gravitational potential energy. So you see, this potential energy is associated with the state of separation of two bodies which show attraction one another by the gravitational force. In same way, what is electrostatic potential energy? Electrostatic means there is a separation of electric charges. Charge under rest condition. Suppose two charges under rest condition with a separation R. So there arises the interaction between two electric charges, there arises potential energy which is named as electrostatic potential energy. And elastic potential energy, that is the state of, this potential energy is associated with the state of compression or extension of elastic, that is spring-like object. So potential energy are mainly classified in 3 categories. Now according to our definition, what we can write mathematically? Write it, very important this one, student. There is a potential energy, change in potential energy, actual change in potential energy, that is equal to negative of work done by the conservative force, negative of work done by the conservative force. This is the actual definition of change in potential energy. So change in potential energy is generally represented by U. So change in potential energy is represented by del U, that is equal to the negative of work done, and this work done with the help of which force? Not non-conservative, conservative force. So write minus of W. Okay, and you know, when a force, suppose a force F applied on a body, and the body displaced through a displacement del X. So you know the meaning of work done, force into displacement. So you can write here, that is del U del u is equal to minus of integration f dot dx, and where this integration must be the lower limit, suppose xi, and the final limit, that is xf. Here suppose f is a function of x, that is force is depends on x, that is a position. Okay, so this is the actual definition of change in potential energy. So in case of change in potential energy, here you can write uf minus ui, that is equal to minus xi to xf f dot dx. Now you just feel it. Suppose this is a ground, the body is placed, suppose mass m, at a height h1, this is the height h1 with respect to ground, and then the body raised in second condition, body is placed here at a height h2, this is the height h2 with respect to ground. Now what is, when the body is moving from, rise from this position to this position, what is the change in potential energy? You say, what is the change in potential energy? There is the, for here the potential energy, that is initial potential energy, is equal to mg h1, weight of the body, that is mg, and the height, that is h1. And what is the final potential energy? Final potential energy, that is height h2, so uf will be mg into h2. Now what is the change in potential energy? uf minus of ui, that is mg common, h2 minus of h1. So this is the change in potential energy when a body rises from height h1 to the height h2 with respect to ground. Now you see here, if we calculate work done, the gravitational force is directed downward, the gravity applied force in the downward direction, and the force expression, that is mass into acceleration due to gravity, and the body displaced from this height. So here displacement, that is body height changes from this is the change in height, so this is h2 minus of h1. So this is the displacement and this is the direction of force. So force and displacement are in opposite direction, so here angle, you see. So what will be the work done? Work done, that is equal to force into displacement, that is f ds cos 180, cos 180, that is minus f dx, and minus f, that is mg, and what is dx? The displacement. You see the total height h1 minus of this initial height, sorry, total height h2 minus of this initial height, that is h1. So this one is h2 minus of h1. Now you just simplify, there is a negative sign, okay, you simplify it, mg, and when this negative sign will be inside here, this one will be h1 minus h2. Now you see, when we calculate the change in potential energy, our expression, that is this one, mg h2 minus h1. And again in this case, when we calculate the work done, our expression is mg h1 minus of h2. So what is the relation? You see here mg h2 minus 1 h1, and here mg h1 minus h2. So the relation is this change in potential energy is equal to the negative of work done. Here work done result mg h1 minus m2, but when we take a negative sign, this one will be mg h2 minus h1. So this is the actual definition. Now from this definition you can write another thing. You see, for small change, what we can write? This is del u, there is a small change in potential energy, and this is the minus of del w. Okay, now you see, that is del u is equal to, what is del w? Force into displacement minus f, and displacement is x dx. So from here you can write f, that is equal to minus of del u by del x. This is the relation. You see, this is also an important relation. This is del u by del x is named as potential gradient. This is the potential, change in potential with respect to position. This is named as potential gradient, and this one is the negative. That is negative, right? Negative value of potential gradient. Negative value of potential gradient shows or gives what? The force. Shows force. Okay. Now from here, if I say the force is, the force is vector quantity. Suppose F is vector, that is Fx I cap plus Fy j cap plus Fz k cap. Now if I say what will be the value of Fx, that is the x component of force. So from this equation you can write Fx is equal to minus del u by del x. What is the value of Fy? Fy equal to minus del u by del y. Similarly, what is Fz? Fz is equal to minus del u by del z. Del x, when force depends on x, you can write force into displacement dx, but in general form, that is position vector dx equal to dx I cap plus del y j cap plus del z k cap. So the x component of force, that means the partial differentiation of u with respect to x. For Fy, the negative value of partial differentiation of u with respect to y. For Fz, the negative value of partial differentiation of u with respect to z. Okay, let's take one problem related to this thing. Suppose force value given, F vector, suppose F equal to 2, okay, you write this one, 3x square, suppose. Okay, and initial potential energy at x equal to 1, this value is given, suppose 10 joule, and you have to find final potential energy at x equal to you write 2. Okay, this is the question. See, force value is given, initial potential energy at x equal to 1, that is 10 joule given, and you have to find out the final potential energy at x equal to 2. So you know the formula. According to our formula, final potential energy minus of initial potential energy is equal to minus of work done. So from here you write uf minus ui is equal to minus of integration xi to xf f into dx. Now that is uf minus of ui is equal to minus of, here xi, there is the lower limit 1, and the xf, that is upper limit 2, f, that is 3x square into dx. Now you just simplify this one. So this one is minus 3 outside common, minus 3 x square into dx, that is, I think all of you know this part, that is x cube divided by 3, 1 to 2. You take 3 outside, that is 3 by 3, and this one is x cube, that means 2 to the power 3 minus of lower limit, that is 1 to the power 3. So this part is cancelled out, 2 to the power 3 8 minus 1 to the power 3, that is 1. So this value is 7, but you see there is a negative sign, negative. So this is minus 7. So uf minus of ui, this value is minus 7. Now what is uf? Uf equal to, you see, ui minus 7. Now what is the value of ui? Ui value is given 10 joule minus 7. So the final potential energy, that is 3 joule. Okay. So these types of problem is important, student. But remember one thing. Okay, let's take one homework. Suppose this force value is given like this way. F equal to 2x I cap plus 2y j cap. Initial potential energy at x equal to 1 10 joule. You have to find out the final potential energy at x equal to 2 joule. So this is your homework. Okay, solve. So for solving this part, at first you have to use same formula, but here you see f into dx here. So you have to take another form. F into dx, that means the fx into dx. Here f has two components, x and y. So in the place of fx, you have to use 2x dx, again minus of fy dy. Fy, that is 2y with multiple of dy. Okay, you solve it. Okay. Now we will check the principle of conservation of mechanical energy. The principle of conservation of mechanical energy when a conservative force acts on a body. You write the statement. When a conservative force acts on a body, the total mechanical energy, that is the sum of kinetic energy plus potential energy, is always remains constant. Write it. The principle of conservation of mechanical energy. When a conservative force acts on a body, condition applied, when a conservative force acts, the total mechanical energy, within bracket write the sum of potential energy and kinetic energy, is always remains constant. Okay, how? You see, if force which is function of x is applied on a body, is applied on a body, and the body displace, and the body displace del x, then according to work energy theorem, according to work energy theorem, we can write what? Theorem, we can write, you know the work energy theorem, work done is equal to change in kinetic energy. So suppose change in kinetic energy del K is equal to amount of work done, and work done, that means force into displacement. Here force applied F, which is a function of x, that means force is depends on x, and the displacement, that is del x. Suppose this is our equation number 1. And again you write, when a conservative force acts, according to definition, what we can write? There is the change in potential energy is equal to the negative of work done. This is our definition. And the negative of work done, that means minus fx into del x. Suppose this is our equation number 2. Now you just compare equation number 1 and 2. Here del u, that is minus of fx del x, and fx del x, that is del k. So if we use equation 1, then you can write del u is equal to, there is a minus, and fx del x, that is del k. So from here you can write del k plus of del u, that is equal to 0. So take a common, del k plus u, that is equal to 0. Change of kinetic energy plus potential energy 0. That means the sum of kinetic energy plus potential energy is equal to constant. That's why the change in potential, the change of kinetic energy plus potential energy is 0. So you can write the initial kinetic energy plus initial potential energy is exactly equal to final kinetic energy plus of final potential energy. This is the proof of conservation law of mechanical energy when a conservative force applied on a body. That means in any force, kinetic energy, any energy, kinetic energy or maybe potential energy changes from one state to another state, but the summation of kinetic energy and potential energy is always remains constant when a conservative force acts on a body. Now we will prove this theorem. That is the conservation law of mechanical energy when a body is freely falling. So our next topic, write it, will prove the conservation law of mechanical energy for a freely falling body. So see, give the heading. There is a conservation law of mechanical energy, conservation law of mechanical energy for a freely falling body. Okay, suppose this is the surface, earth surface, body is situated here initially. A body is falling from this height. This is the position A, suppose. The mass of the body M. And you see, this is the another position. Suppose this position is B and this position is C. This height is represented as H. this height is represented as x. So this height will be obviously h minus x. Now we will consider 3 points. At point A, B and C, we will find out the potential, the total mechanical energy at point A, the total mechanical energy at point B, and the total mechanical energy at point C. And if I give the answer, the total mechanical energy at point A, B and C, that is same, so we can easily say that the mechanical energy is conserved. So find it. At first you find the total mechanical energy at point A, and the total mechanical energy, that means the sum of kinetic energy plus of sum of potential energy. So when a body is falling from point A of mass k, initial velocity, what is the initial velocity? Initial velocity is 0. So at point A, right, at point A, the initial velocity that is equal to 0. So what will be the kinetic energy here? Kinetic energy, that is half m v square, but here velocity is 0, so kinetic energy results 0. Now what is potential energy? You write kinetic energy and then you write the potential energy U. Potential energy, that is mass, acceleration due to gravity g, and you see the height. When the body at position at A, the total height you see, that is h. So this is h. Now you just add it. The total energy that is equal to k plus of u, that is 0 plus of mgh, that is total energy is mgh. So this is our first condition. At point A, the total energy, total mechanical energy is mgh. Now find at point B. Okay, find it at point B. Now see, when a body is falling from point A to B with velocity v, suppose at point B the body attained velocity v. Here you have to find out what is the value of this velocity. After that you can find out the value of k. So at first you find, when the body at point B, what is the value of velocity. But you see, when the body is coming from A to B, the total distance travel, that is x. So you use the equation, this one, v square equal to u square plus 2as. Now v square is equal to initial velocity of the body, that is 0, 0 plus 2a, that means freely falling, acceleration due to gravity, a is equal to g, and the s is the distance travel. Now from A to B, the distance travel, that is x. So here v square equal to 2gx. Now you can easily find out the kinetic energy, because kinetic energy k is equal to half m v square, that is half m, and v square, that is 2gx. 2gx, 2 cancel out, so this one is mgx. Now you find out the potential energy, u potential energy, that is mass into g, that is mg, and what is height here? The body position B, so the height of the body with respect to ground, this is the height which is represented as total height h, this one is x, so this one is h minus x. So right, that is h minus x. So total energy, same thing, total energy, that is k plus of u, k that is mgx, and u that is mgh minus of x. You simplify, that is mgx plus mgh minus mgx, plus mgx minus mgx cancel, so answer is mgh. At point B, the total mechanical energy is also same, that is mgh. Now you find the same thing at point C. Okay, find it. At point C, when the body is from moving A, B to C, what is the velocity? Suppose the body is attained velocity v dash at point C. Now here you have to find out v dash. So same, that is v dash the square is equal to u square plus 2as. So v dash is equal to initial velocity 0 plus 2a, that means g. And what is distance travels here? You see the body coming from A and the finally body position is C. So the total distance travel this point to this point, that is h. So here v dash the square is equal to 2gh. So what will be the kinetic and potential? Find. So kinetic energy will be half m v dash the square, that is half m, and v dash the square, that is 2gh. 2 cancel out, so this one is mgh. And what is potential energy here? Mass, acceleration due to gravity, and when the body is at point C, you see there is no height, so height is 0, so potential energy is 0. So what is the total energy? Total energy, that is K plus of U, that is mgh plus 0. So total energy is mgh. So you see at point A, at point B, and at point C, at every point the total mechanical energy is same. So finally you can say the conservation law of mechanical energy is conserved. The principle of mechanical energy is conserved in case of freely falling body. And you see when a body is falling from height, initially the body kinetic energy is 0. Kinetic energy is 0, that is the kinetic energy is minimum, but the potential energy is maximum. And the body when falling from like this way, its kinetic energy increases because its velocity increases. Similarly, its potential energy decreases. As a result, the sum of kinetic energy and potential energy remains constant. Okay, now we will draw a graph. How to draw a graph? That is the graph of energy versus height for this freely falling body. Draw it. So suppose y-axis is represent energy and x-axis is represent height. This height 0, this height h, this energy suppose value given mgh. Now you see at the maximum height, when the body at point A, kinetic energy is 0. So maximum height, when the height h, kinetic energy 0. So this is the point for kinetic energy. And what is the maximum kinetic energy? When the body at the lowest point, the kinetic energy is maximum. That is when h equal to 0, kinetic energy is maximum. And what is the value of maximum kinetic energy? This one, mgh. So when height 0, the kinetic energy is maximum. And when height h, the kinetic energy is minimum. So this is the graph for kinetic energy. In same way, you see when the maximum height body attained, the potential energy is maximum and the value is potential energy, that is mgh. So when height h, the potential energy is maximum, that is this value is mgh. This is the point of potential energy at height h. And when the body at point C, that is when height is h equal to 0, the potential energy is 0. So when height is equal to 0, the potential energy is 0. So this is the point. And potential energy varies directly with height. So this is the graph of potential energy. This is the graph of potential energy, that is U. And then this is the graph of kinetic energy, that is K. And what is the graph for total energy? Total energy is at point A, at point B, at point C, at every point there is mgh. So always the total energy is mgh. So this is the total energy. This is the total energy graph. And the total energy graph is parallel to this height, because at every position, at every position of the body, total energy remains constant. This is the theory which I proved here. So this is all about this proof of mechanical energy for a freely falling body. So I think this part is clear to all of you students. Complete it and you solve the given homework and tell me. Today I'm ending here. Tada.